Hey guys! This video we're going to go over lesson 15 in the Calc manual on continuity and differentiability. So in pre-calc you talked about continuity and you talked about the fact that it was when you can draw a graph without lifting your pencil from the paper. Well, in calculus we're going to go ahead and formally define continuity. This is a very important definition. In order for a function to be continuous at x equals c, all of the following must hold. First, the limit as x approaches c must exist. This means the left-hand limit and the right-hand limit matched, therefore the limit as x approaches c of the function exists. That's part one. Part two, or criteria number two, is that the function evaluated at c also exists. So right now we've got that the limit as x approaches c exists, so the left and right hand limit agree. The function evaluated at c exists, and last but not least, the limit and the function value must be the same. This is the big kicker, is that the limit as x approaches c of the function, that value and this value must be the same value, or else the function is not continuous. Okay? So again, for some value at c, as x gets closer and closer to c, both from the left and the right, we approach a limit L1. Let's say you plug c into the function, you get a value called L2. Well, L1 must equal L2. That's what this is saying. This value that you get here must be the same as this value that you get there. If a function is continuous at all values of x, then we say that it is a continuous function. A function can be continuous in certain sections and discontinuous in others. So if we're only looking at specific intervals, it can be continuous in a specific interval but discontinuous in others. So if we take a look at the following graphs, we're determining whether f of x is continuous at the given value of c. And each of the graphs there's a given value of c that you are looking at. We're determining whether it's continuous there and which of the three continuity rules it fails. So remember, rule number one is the limit rule, rule number two is the f of c rule, and rule number three is that rule number one and rule number two are equal, which is, the big kicker here. So if we look at A, the limit as x is approaching 1 from the left and the limit as x is approaching 1 from the right do not agree. So the function is discontinuous and it is breaking rule 1. So it's breaking rule 1 and it's discontinuous. This function is limit as x approaches 1 from the left and from the right agree, but f of 1 does not exist. So this one is breaking rule 2. So discontinuous. All right. At 0, limit as x is approaching 0 from the left, limit as x is approaching 0 from the right, and f of 0 is all right there at that red marks the spot, red x marks the spot. This is continuous at 0, and all three rules were met. The limit as x is approaching 0 from the right and from the left are equal, the limit exists, f of 0 exists, and f of 0 is equal to the limit as x is approaching 0. If we take a look at D, limit as x is approaching 0 from the left and from the right agree at this value. F of 0 is this value, and it was the same for 1 and 2, so 1 and 2, rule 1 and rule 2 are equal in the same value. So this is also continuous, and all three rules were met. All right? So I would like you to do E, F, G, and H. Pause the video now, and then I'll give answers for those. Okay, so I'm assuming you've paused the video. E is discontinuous because it did not meet rule number 1, and it did not meet rule number 2. F of 2 does not exist, and the limit as x approaches 2 from the left and from the right do not exist. In the next one, F, it does not meet rule number 3. The limit as x approaches 2 from the left and the right is infinity on both ends, even though infinity also means does not exist. So it could be rule number 1 and rule number 3 here. But let's say that you called that infinity. F of 2 is defined here at whatever this value is, but the limit and the function value are not the same. So we can say rule 3, we can say rule 1 and rule 3 since the limit is infinite. G breaks rule 2. Oh, no, it doesn't, because we're looking at -2, not at the whole. So if we're looking at -2, it's actually continuous at -2. Since the limit as x is approaching -2 from the left and the right exists, f of -2 exists, and that value and the limit value are the same. If we look at h, we're looking at -1. The limit as x is approaching -1 from the left and from the right do not agree. Therefore, we are breaking rule 1, so it is discontinuous. Even though f of c does exist, the limit does not exist. And you can read here to see how example A is an example of step discontinuity or jump discontinuity, and example B is an example of removable discontinuity. We call that a hole. All right? And in algebraic form, hopefully in algebra you saw how holes happen, but usually that's when you have a rational expression and then you factor the numerator and those x plus 2's cancel. You end up with x minus 3, but there should be a hole when x is -2. That's how holes happen. So let's take a look at the next page. We have a handy little chart at the top of the page that examines functions in algebraic form and kind of summarizes the following conclusions. First, all polynomials are continuous. So every polynomial is continuous. Fractions in the form of y equals f of x over g of x are discontinuous whenever g of x is equal to 0. It makes no difference if g of x cancels out, because when it does, like I just told you, it creates a hole or a removable discontinuity. So all polynomials are always continuous. Fractions are always discontinuous wherever the denominator is equal to 0. If you have a radical that's an odd root, so third roots, fifth roots, and so they're continuous everywhere. If you have a radical with an even root, they're discontinuous whenever the radicand inside the radical is negative, because we cannot have negative even roots. We cannot take the even root of a negative number, sorry. Trig functions in the form of y equals sine and y equals cosine of an angle are continuous everywhere. And exponential functions in the form of y equals ab to the x, so e's and 5 to the x and whatever, they're also continuous everywhere. So I would like you to work on examples 2A through F on your own as a review of pre-calc and using the summary above, and check your answers in the binder tomorrow, because we are going to move into looking at these questions. So go ahead and do example 2 on your own, and I'm going to move on and look at these questions. So we wish to determine if piecewise functions are continuous. We want to see if these piecewise functions are continuous. It is possible and usual that both pieces of the piecewise function are continuous, but we need to check continuity at the value where the rule changes. This is the rule. So we want to look at continuity at 1, when we change from one function to the other function, okay? And we're going to check for continuity using the definition of continuity, which is 1, that the limit exists, 2, that the function at that value is defined, and 3, that number 1 is equal to number 2. So using that definition, let's run a test here. So first test. First, we're checking that the limit exists. So we're going to check the limit as x approaches 1 from the left and the limit as x approaches 1 from the right of f of x to see if the limit exists. All right. So x is approaching 1 from the left here. So the limit as x approaches 1 from the left is 1 minus 3, which is -2. And the limit as x is approaching 1 from the right is here, 1 minus 1, which is 0. The limit as x approaches 1 does not exist. Therefore, f of x is not continuous at x equals 1. Okay, so where the rule changes right here at x equals 1, the function is not continuous. So let's check the next one, and then I'll have you do the next two on your own. So we're going to check the next one here. All right, so let's check, first let's check rule 1, or part 1 of the rule, not rule 1. The rule has 3 parts. So part 1 of the rule is to check the limit and make sure that it exists. So we're going to check the limit as x approaches 2 from the left of f of x, and we're going to check the limit as x approaches 2 from the right of f of x. Okay. X approaching, oh, negative 2, not 2. Because the rule changes at negative 2, so we need to check for continuity there. Okay, coming at negative 2 from the left, that's right here. So that is 4 minus 6 minus 2, which is negative 4. And here is the right, coming at negative 2 from the right, so that is positive 4 with negative, so negative 4. So the limit exists. Let's check f of negative 2, and the limit is negative 4, of course. Okay, so the limit, let me write that down, x approaches 2 of f of x is negative 4. Perfect. All right, f of negative 2, that's going to happen right here because this is x is less than or equal to negative 2, so we're going to plug negative 2 into this piece of the function, and we already know that answer is negative 4. So that is rule 2, part 2 of the rule. So part 1, the limit exists. Part 2, f of that value exists. And part 3 is that the limit as x approaches negative 2 is equal to f of negative 2, and that is also true because both were negative 4. So therefore, f of x is continuous at x equals negative 2 and everywhere else. Okay, and everywhere else because we've got here a polynomial, so we've got continuity everywhere, and we've got continuity where the rule changes. There's no jump or hole or anything like that. There's no jump, and so it's continuous at x equals negative 2 and everywhere else. So go ahead and try 5 and 6, and then I'll give answers. I'll tell you right now that for this one, f of x is not continuous at x equals negative 1, so I want you to determine which rule, or which part of the rule did not work. And for this one, f of x is continuous at x equals 4. It is continuous at x equals 4, so you should be able to do this and all 3 parts should work.